Now, one of the things to keep in mind when you think about what we talked about last time, which is Stokes' theorem, is initially it looks like it's a really hard problem, but the point of Stokes' theorem is to show you how to transform a problem from one setting to another setting. And we do examples which are challenging just to have you sort of experience what the different possibilities are. However, were we to test you on it, you will see that once you apply the tool, if you apply the tool correctly, the resulting integral that you do, either the line integral or surface integral or surface integral over a better surface, they'll be very straightforward. And so what we really want to do is test, do you understand the tool? So make sure you understand the tool. That's important. Now, where did Stokes' theorem come from? It came from Green's theorem. And there's actually two variations of Green's theorem. So one variation of Green's theorem, which is one where Stokes' theorem comes from, is when you integrate along a curve of f dot t. But there's a second variation of Green's theorem, and so we should remind ourselves of what that one says. It says the following. Suppose you have a region in the plane. So some sort of shape. So here's our region in the plane. This is a two-dimensional picture right now. So we have our two-dimensional picture, our region in the plane. And what we can say is the following. I can think about this as a region, and with that I can have what I call the normal vectors. So you see this n here. The difference between last time and today is that the t became an n. Now when we talk about n is normal. That means perpendicular. So what we have is that to this surface there are perpendicular vectors. And we always point out. I'm sorry, I said to the surface. I meant to say to this curve. I'm getting ahead of myself. So I have these normal vectors. And now what I can do is I can integrate around the boundary f dot n. Now the question is, what is the integral of f dot n? So the answer is, whenever you see an integral that has the form of f dot n, regardless of the context, you can always say this is interpreted as flux. And so what's happening here is you have this vector field f. So you can think of this vector field, you might think of it like a fluid flow. So you have, if you have these little arrows representing how things are flowing. So if I do f dot n, what's happening is it's saying how much is flowing through my region. So I have this somehow flow happening, and I'm saying, let's look at this particular region. So the first integral f dot n, says, let's look at the boundary. What's flowing through the boundary? We can show, and we actually did this when we talked about Green's theorem, that this is equal to the integral over the interior of the region of the divergence of f. So that we can transform an integral on the boundary to an integral in the interior. And the nice thing is, it really is a variation of the fundamental theorem of calculus, because if you think about what divergence is doing, that's essentially taking a bunch of partial derivatives. So if I want to know something about the derivative on the interior, I can look at what's happening with the function on the boundary. All right, so the question is, can we generalize this to 3 dimensions? And the answer is yes, and that's the second part here. This is called the divergence theorem. Sometimes it's called Gauss's divergence theorem. So what's going on here? Well, you go up to the 3rd dimension. But now, instead of a region in the plane, what you have is a solid. And so we have some sort of solid. So all my solids tend to look somewhat bean shape. So here's our solid in 3-dimensional space. And we can do as we did before, which is namely, if I have a solid, I can talk about the normal vectors to that solid. So we always think about these as the outward normal vectors. So another way to think about having these outward normal vectors is to say, I can go stand on the surface of this solid. All right, so I have these outward normal vectors. These are my little ends sticking out. And again, I can have this flow coming through this function f. And the divergence theorem It's really beautiful. It says, if I want to compute f dot n, the flow through the surface of the surface of the solid, that's the same thing as integrating over the whole solid the divergence of f. So in some sense, if you look at going from our Green's theorem to our divergence theorem, we've essentially added an integral sign. Because here you'll see it's a 1 versus a 2-dimensional integral. Here it's a 2-dimensional versus a 3-dimensional. But the philosophy is still the same. Now, we're not going to prove it. If you want to prove it, we have a wonderful major on campus that you can take called math. It's a great major, wonderful major. And you can learn all sorts of fun, exciting things. So once you understand this is essentially it. This is the tool. So the tool, you'll see it's a box. Whenever you see a box, you should remember what's in the box. So the tool is, if I'm computing flux through the boundary of a solid, which is a surface which bounds a solid, I can convert that to a triple integral over the solid. So almost always, and when I say always, 99.99% of the time in the problems that you'll see, and we're not trying to trick you, we go from an integral on the surface to an integral on the solid. So this is what we want you to remember. So it's not so bad. And we'll do some examples of this. Now, how do you recognize these types of problems? There's a few key things to look for. One thing to look for is to look for the word solid. So if you see something with a solid, this is a potential problem. Now, not everything that says the word solid is a divergence theorem. Don't get too caught up on it. Because, for example, we had a recent exam, and we talked about solid, where we had a cone, but we did like an inertia problem. So it's a solid plus one other thing has to happen. You need to have some integral expressed in this way. Now, they might actually write down an integral of some crazy function .n, dsa, or they might phrase it as compute the flux. So if you see the word flux, that's a divergence theorem. So just look for these two things. Look for a solid and either the word flux or this type of integral set up here. And once you have those two things, you're good to go. Well, let's try it. Let's see what happens. So our first example. Let G be the surface of the sphere of radius 1, centered at 0, 0, 0, with outward pointing normals. Find the integral on our sphere G, 2x, yz, z squared, n dsa. So you can see we're in the right setting because we have this function f. So in our case, this is our f, 2x, yz, z squared, n. On a side note, again, sorry, I keep jumping to side notes. Eventually, we'll jump so far, we'll get back to where we started. Sometimes you will see a different notation. I like this notation just because it's easy for me to understand. A little bit of surface area. Other places you'll see it. I think the book uses sigma. So if you do run across something that says d sigma, just know that that means it's a little bit of surface area. Okay, so, but here we go. It's the surface of a sphere. A sphere doesn't say the word solid, but it's a solid sphere. All right. So I have my sphere, unit sphere. And in particular, notice that there's a difference here between Stokes' theorem versus divergence theorem. This is something else to keep in mind. So when he had Stokes' theorem, we again dealt with an integral of a surface integral. Now that was a very special type of surface integral. We had the curl of f involved in that one. But there's something else about the surface. See, when we did Stokes' theorem, we had a surface that had an edge. So Stokes' theorem deals with surfaces with edges. Because what we do is we push the surface integral to the integral on the edge of that surface. Notice that this surface, there's no edge. And that's a difference there. So if you have a surface without an edge, that's another sign we're talking divergence theorem. All right, so divergence theorem says that this integral of g, is equal to the integral over the whole sphere, we'll call it S, of the divergence of 2x, yz, z squared, dv. So let's compute the divergence. So this is also a test of, do you know how to compute divergence? So divergence, remember, we start with a vector valued function. We're going to end up with just a normal function, scalar function. And what you do is you take the right derivative of each component. So in other words, in the first slot, you take the derivative with respect to x. And what do you get? You get 2. In the second slot, we take the derivative with respect to y. And what do we get there? We get z. In the last, we take the derivative with respect to z, and we get 2z. All right, so this becomes the integral. Well, there's really two things. I'll separate it. 2 dv plus the integral over our solid 3z dv. Now, one of these two integrals is easy, and the other one is easy. All right, which one do you want to do first? I don't know what you're thinking. The easy one. All right. Well, maybe I'll say the first one is a little bit more obvious as to why it's easy. When I compute the integral over a solid of twice dv, what am I computing? Twice the volume. You can pull the 2 out. Now, do we know the volume of a sphere? It's 4/3 pi r cubed. And what's our radius? 1. So 4/3 times pi times 1 cubed. Now, I said this one was easy. Now, normally speaking, it can be challenging, but what do you notice about that integral in regards to our region? Think about the solid. What's true?
It's symmetrical.
Yeah, there's symmetry. The solid has symmetry. In fact, the sphere is super symmetrical. Now, what symmetry do we like? Well, oftentimes, don't try to throw out symmetry all the time. Sometimes you just have to bite the bullet, as they say, and do the integral. But in our case, we say, well, you know, it'd be cool if I took a little piece, say, above the xy plane, if it matched with a little piece below the xy plane. And in this case, it does, because I have that symmetry across the xy plane. So the contribution from above the xy plane is the same as the contribution from below, except different sign. So when I put it all together, what happens? I get 0. So this is cancellation. I get 0 by symmetry. So I'll be a little bit cautious when you pull out symmetry. I know some people kept pulling symmetry out when it didn't apply, but you know, when it does apply, fantastic. All right, so what's our final answer? Well, 8. I can write the 8. 8/3 pi. All right, good. I will make another comment here, which is this is a fun chance for us as test writers to incorporate things like spherical coordinates and cylindrical coordinates, because those are sort of the easiest solids to describe. And so you'll often see these problems mixed in with spherical and cylindrical. They don't have to be. You can definitely do this with any type of solid, but you'll see that in many, if not all of our examples that we do tend to incorporate things which are spherical or cylindrical. But again, mostly because those are easy to describe. Okay, so our next example. So given f, it's our vector valued function. So we have this x cubed plus tangent 1 over 100 yz I, y cubed minus e to the x z j, and 3z plus x cubed k. So this is just a different way to write f, where we say, okay, what's in the I direction, what's in the j direction, what's in the k direction. We should be flexible enough to interpret whatever they give it to us. S is the solid where x squared plus y squared is less than or equal to 4, and 0 is less than or equal to z less than or equal to 3. What does that solid look like? Yeah, so this x squared plus y squared less than or equal to 4, that would be a circle of radius 2. But of course, in 3 dimensions, it's a circle of radius 2 going straight up and down. So what we end up with is we end up with a cylinder. Goes all the way up and down. And of course, keeps going. But then we say, aha, don't take all of it. You got to start at z equals 0, and then you got to stop at z equals 3. So we have our shape just the part from 0 to 3. So there's our solid. Okay. Now we want to find the integral on the boundary of our solid of f dot n dsa, where n points outwards from the solid. Of course, it's going to be clear today that all our problems are going to deal with divergence theorem, but let's not take that for granted. What are some things, some clues that tell us divergence theorem? Well, an ugly f, yeah, that's a good sign. If you have like an ugly f, that's usually a sign, don't actually use this f. You want to do something to it. Other clues, we see the solid, we see a flux. And when we see all these pieces together, we're like solid and flux, that's the divergence theorem. Ugly f, that's a clue that we're not supposed to be doing what it actually asks us, but we should use the tools to modify the problem. All right, so this is going to be, according to the divergence theorem, we take the integral on the boundary of f dot n dsa. That's become the integral over the whole solid of the divergence of f, or if you like, del dot f dv. So let's take our divergence. We come to our first slot. What's the derivative with respect to x? 3x squared. Go to our second slot. Derivative with respect to y? 3y squared. Go to our last. What's the derivative with respect to z? 3. All right. And so here, you can see that the parts that we were like, oh, I don't really have to want to deal with this tangent of 1 over 100yz, we don't have to. It goes away. Ah, happy days. Happy days. All right. Well, we still have to integrate it. And, well, can't just, no easy way out. So what would be our next step? What would we do next to make progress in our integration? Yeah, convert to cylindrical. Exactly. Because we have a cylinder here. So if we come here, we say, all right, let's just look at our bounds. Well, we see it's fully symmetric when we spin it around z. So that tells us that theta is going to go between 0 and 2 pi. Our r, well, that says how far do you come out from the origin. Now, when you go into 3 dimensions, you can really say how far do I come off the z-axis. We always come off the same amount. Namely, we go anywhere from 0 up to the radius of the cylinder, which is 2. And you can get it by saying, okay, r squared is less than or equal to 4. And then z, well, that's easy because in cylindrical, z is z. So 0 less than or equal to z less than or equal to 3. And of course, we know that dv is r dz dr d theta. Okay. And of course, one more thing, factor out the 3 so we can get ready for our upcoming substitution. So this will be an integral, integral, integral. Our function becomes 3r squared plus 3. Our dv is r dz dr d theta. Theta goes 0 to 2 pi. R goes 0 to 2. And z goes 0 to 3. Now, at this point, we can say, okay, this is the kind of integral that we like. Now, you can do it one layer at a time, and if that's what you prefer, go ahead and do that. For me, whenever I see that all the bounds are constants, then what I like to do is I just say, let's just pull it apart and just do each one individually. Now, all the bounds have to be constants in order to do it. If they're not, work through it one layer at a time. But for us, we can say, all right, well, this is integral 0 to 2 pi d theta. So that's the only thing that involves theta. Then we have integral 0 to 2. And I'll multiply this r through. So we get 3r cubed plus 3r dr. And then the last part is 0 to 3 and dz. Well, two of these we can do without much work. Integral 0 to 2 pi d theta? Yeah, 2 pi. Integral of 0 to 3 dz? 3. All right, now this middle one, we have to do a little bit of work. What's the integral of 3r cubed plus 3r? 3/4 r to the 4th, and 3/2 r squared. Good. And this one we evaluate from 0 to 2. Well, the good news is if you plug in 0, we're going to get 0. If you plug in 2, 2 to the 4th, 16. If I take 16 divided by 4, that's 4. Times 3 makes 12. 2 squared is 4. Divide that by 2. That gives me 2. Times 3 makes 6. So I get 6. Or, that's really 18. So I have 2 pi times 18 times 3. And if you multiply all those together, you end up with 108 pi. Whoop, there you go. Because 18 times 3 is 54. You double 54, you get 108. All right. Good. Good. So you see, this looks like a terrible problem, but then all of a sudden it's like, oh, that's not so bad. That's our goal. You want to walk out of the final saying, that's not so bad. All right. Another one. Let Q be the solid of points satisfying x squared plus y squared plus z squared is less than or equal to 4, and z is less than or equal to the root of x squared plus y squared. Find the integral on the boundary of this solid of some crazy thing dot n dsa, and n points outward from the solid. Again, we go through our mental test. What's our tool? We see we have a solid. We're integrating on the boundary of that solid. And it's a something dot n, which means it's a flux. All right, so divergence theorem. Let's look at our solid for a few moments. It really comes from two pieces. So x squared plus y squared plus z squared less than or equal to 4, what does that tell us? Yeah, we want to be inside a sphere. And the inside comes from the less than or equal to. So in particular, we want to be inside a sphere of radius 2. So I have a sphere of radius 2. Now let's go to this one. Z less than or equal to square root of x squared plus y squared. All right. Well, what does z equals the square root of x squared plus y squared look like? What is it? Z equals r, which is? It's a cone. Yeah, so this is the cone. So it's a cone that comes up something like this. Now, what does the inequality tell us? So here we say, okay, we're inside the sphere. Where do we want to be in relationship to this cone? So it says less than or equal to. So am I in the cone or am I below the cone? I'm below. Essentially, you can think of this as saying z is below this cone. So that says I want what's underneath. All right. Well, now we do our sort of cross our eyes and see where do these things overlap. And what we end up with is that our shape, it looks something along the lines of the following. Where what we've done is we've taken a sphere of radius 2 and then we've drilled a cone out of it. So that's our shape. Okay? Something like that. So it's a sphere, but you drilled the cone out of the top. All right. Well, it's a little different. A little bit different. All right. Well, we can probably still figure it out. We're pretty good. We've practiced. We've gone better. All right. So now we see our shape. Let's figure out what our integral is going to become. So we're going to apply the divergence theorem. So this becomes the integral over our solid. Come to the first slot. What's the derivative with respect to x? Well, y squared. See this terrible thing here? There's no x. So that's good. We got rid of the really unfortunate looking part. Go to the next slot. What's there with respect to y? X squared. Go to our last slot. What's there with respect to z? Z squared. Now, we look at our function. We're integrating y squared plus x squared plus z squared. We look at our shape, where we have a sphere with the cone drilled out. Where do we go to actually do this integral? What's our next step? Spherical. Now, what's some clues that spherical is the way to go? Well, yeah, the x squared plus y squared plus z squared is a great clue. What does x squared plus y squared plus z squared become in spherical coordinates? Rho squared. Yeah, because rho is the square root of x squared plus y squared plus z squared. So rho squared is x squared plus y squared plus z squared. That's nice. That's a very simple function in spherical coordinates. Now, of course, the other clue is the fact that it's a sphere, our region. So that's a pretty strong clue. All right, hard to ignore that one. Now, when you're doing spherical coordinates, sometimes it can be tricky to figure out the bounds. Now, at least one bound is fairly straightforward, which is the theta. We see that we can spin around the z-axis. It's fully symmetrical all the way around. So what does that tell us about our theta bounds? 0 to 2 pi, yeah. 0 less than or equal to theta, less than or equal to 2 pi. Good, that's one of our bounds. Now for the other bounds, I often find it's very convenient to look in a slice, because oftentimes when I see the whole picture, it's a little bit hard for me to figure it out. So when I talk about a slice, I'm going to say here's my z-axis, and I like to call this my r. So I look at a ZR slice. It doesn't really matter which theta I'm picking. Essentially I'm saying pick a theta, look in a slice, and see what you get. The cone here becomes z equals r. So there's our cone. Now, the sphere, well, it becomes a circle. So what we're going to have is it's going to come off here. We don't include that part, but then we do include this part down to below. And so our shape is being formed by spinning this part around. So there's where our shape is coming from, is spinning that around. Now we're ready to talk about our other two bounds. So how about phi? Well, phi equals 0 tells us how we come off the z-axis. So phi equals 0 is straight up the z-axis. I don't hit anything until I hit z equals r. Z equals r corresponds to what angle for phi? Pi fourths. So I start at pi fourths. Because I don't see, if I come out an angle below pi fourths, I don't hit anything. And then what's going to happen is I'm going to keep turning. I keep hitting my region. In fact, I hit it until I hit what angle? When do I stop? Well, pi halves would be here. So I still have more to go. So where do I need to go? I need to go all the way to pi. So pi halves would be if I stopped on the xy plane. So if you're going below the xy plane, you're going to go past pi halves. So you have to be a little bit careful there. All right. So there's phi. Now the last thing, rho. So for rho, we always like to think about it as how do you come out from the center, the origin. You always come out from the center in a straight line until you hit your bounding surface. Well, so we come out, start at 0, and we go until we hit what? We go until we hit the sphere, which is at 2. So 0 is less than or equal to rho is less than or equal to 2. Okay, so there's our setup. And I suppose the last thing we should say is about dv. Do you remember what dv is for spherical coordinates? Rho, rho, sine of phi, d rho, d phi, d theta. It's going to get into your brain, that song. You're not going to be able to get rid of it. You're going to go home during break. You're going to be nestled around the fireplace, talking to your family. They're going to say, so what did you learn in Calc 3? And you'll say, let me sing you a song. I'll tell you what I learned. All right. Okay, so let's put it all together. So we're going to have that this is the integral, our function, rho squared, our dv, another rho squared, sine phi, d rho, d phi, d theta, theta 0 to 2 pi, phi pi over 4 to pi, and rho is 0 to 2. So from here, again, this is a really nice integral because all the bounds are constants, which means that we can just really pull it all apart. And if we do that, we get the following. Integral 0 to 2 pi of d theta, integral pi over 4 to pi of sine phi d phi, and integral 0 to 2 of rho to the 4th. Multiply those together, d rho. Well, the first integral, what do we get? 2 pi. Good. The second integral, well, the integral of sine? Negative cosine. Going from pi over 4 up to pi. So, we plug in pi. Cosine of pi? Yeah, cosine of pi is negative 1, but then we're put a negative in front of that, making that a positive 1. Subtract. Cosine of pi fourths? Root 2 over 2. All right, last part. Integral of rho to the 4th. Rho to the 5th over 5 from 0 to 2. Plug in 2. Well, that'd be 1/5 times 2 to the 5th, also known as 32. Now, well, I don't like a fraction there, so I'm going to go ahead and take this 2 here and just multiply it in. So I have a pi. Then I have a 2 minus root 2. Again, I took this 2, multiplied it into the 1 minus root 2 over 2. And then I have another 32, and it's all over 5. You make an excellent point. Easy to fix that. Thank you. Yes, you are correct. Thank you. All right. I would have gotten partial credit. This is the advantage of not having it be multiple choice, because we would have put a minus, and you'd be like, ah! So, okay, good. Or even worse, if you use one of those like exams where it's using the homework system. Oh, one small mistake in the syntax. Well, sorry, you didn't know what you're doing. Too bad. Okay, next one. Let t be the solid with 0 less than or equal to z less than or equal to 1, and x squared plus y squared less than or equal to 1 plus z squared. We actually did this solid, well, not the solid, but we did the surface. Do you remember what this surface is? It was the other day. I know Monday seems like a long time ago. Hyperboloid. This is the hyperboloid. A hyperboloid of one sheet. And so I'll go ahead and just sketch what this is doing. What's happening is it has something that looks kind of like this. So this is our shape. All right. On an exam, we probably would sketch this one because it's a little bit less common. We tend to expect that you know how to draw spheres, for instance. So we tend not to give you pictures when the problem is a sphere. But when it's an unfamiliar shape, we throw a picture. Okay, so we have this solid. Ooh, see the word solid. And we have n is outward pointing almost to the bounding surface, g. Okay, so g is our surface. And we want to find the integral of this crazy looking thing, dot n. All right, well, a solid, and we're computing flux. So this is divergence theorem. And of course, we don't want to do this surface integral because first off, that does not look fun, that surface. And second off, the pieces look terrible. All right, so we apply the divergence theorem. So this is going to be equal to the integral over our solid. Our solid is called t in this case. Come to the first slot. What's the derivative with respect to x? 0. Nice. Favorite number. Okay, go to the second slot. Derivative with respect to y? 0. 2 for 2. Oh, this is going to be great. Come to the last slot. Derivative with respect to z? 8z. All right, well, that's something. All right, but I think you'd agree that if you saw that, you'd probably say, that's the one I'm going to drop. If you saw this, it's like, full points, here I come. And you see, we didn't go very far. The difference was we knew the tool, and then we applied the tool, and then life is good. Now we have to say, all right, let's integrate. What kind of coordinate system should we use to integrate this? Well, it doesn't involve spheres. Generally speaking, my rule of thumb is if it doesn't involve spheres, probably avoid spherical, because spherical can get messy. But notice that we do have beautiful symmetry around the z-axis. Whenever you have that nice spinning action around the z-axis, that says cylindrical is not an unreasonable choice. And it's certainly better than Cartesian when you have that. So let's go Cartesian. Let's go cylindrical. These morning classes. All right, well, we're almost through it. All right, we'll make it. All right, so again, we'll make our little notes. dv is r, dz, dr, d theta. Let's get our bounds. We know what theta does. Where does theta go between? 0 to 2 pi, because we're going all the way around. Now, to get an idea of the other bounds, let's take a look at our slice. So I have r and I have z. So in particular, what we can do is if we came up here, we could rewrite this expression as r squared. I'm just going to write it as equals 1 plus z squared. Just to sort of see what that looks like. And so what you could say, let's see, am I doing this right? That looks right. Okay, so what does that tell us? Well, it says that z is the square root of r squared minus 1. So what happens is it starts here at 1, and then it kind of goes. It's not a circle. Be careful. Circle would be 1 minus r squared. It's r squared minus 1. So what it is, it's a hyperboloid. Well, that's probably not too surprising. And it goes something like this. And in particular, we stop here at z equals 1. You can figure out, all right, if z equals 1, where do you hit down here? Well, the answer is you'd hit at root 2. Because if z equals 1, you get r squared equals 1 plus 1. Now we have to make a choice. And I know that up to this very moment, we've always been consistent about what to do in cylindrical. But I also know that we're good, that we're smart, and that we're capable of doing amazing things. So here's the thing. Would we want to slice this way, which is how we've normally done it, up and down, or would we prefer to slice horizontal? So the difference is, what's the order of integration? So the current way we integrate dz dr would be slicing up and down. Is it better to slice up and down, or is it better to slice horizontal? Horizontal. And the reason it's better to slice horizontal is if you're doing vertical slicing, you see there's a change in behavior at 1. And whenever you see a change in behavior, that means multiple integrals. More integrals to do, the more chances for mistakes. We want to minimize our chances for mistakes. So we want to have as few mistakes as possible. On the other hand, if we go side to side, it's always consistently the same curves. So we're actually not going to do dv equals r dz dr d theta. We're going to do dv equals r dr dz d theta. So we're going to just switch our order of integration. So let's talk about z. Where does z go from? 0 to 1. Where does r go from? Well, now we need to solve for r as a function of z. So r squared is 1 plus z squared, which tells us r is the square root of 1 plus z squared. So I go from 0 out to the square root of 1 plus z squared. So now we can set up our integral. So this becomes integral, integral, integral. The 8z in cylindrical coordinates, what does 8z become? It becomes 8z because it's the same thing. All right, 8z. And then we've got our dv. That's r dr dz d theta. Theta goes 0 to 2 pi. Z goes from 0 to 1. And then r goes from 0 to the square root of 1 plus z squared. All right, so we do our integral. Well, what's the integral with respect to r of 8z times r? Well, our integral with respect to r, the 8z is a constant. So integral with r is r squared over 2. I can put the over 2 into the 8, so that would be 4z r squared. Evaluate from r equals 0 to r equals the square root of 1 plus z squared. Now the nice thing is, plug in r equals 0, you get 0. When you plug in r equals the square root of 1 plus z squared, well, we're squaring r. So what does that tell us? Well, we get 0 to 2 pi, 0 to 1 of 4z times 1 plus z squared, dz d theta. And so to integrate that, well, we multiply the 4z through. So this is 4z plus 4z cubed, dz d theta. Now, that's not an unreasonable integral. So what's the integral of 4z plus 4z cubed? 2z squared and, yeah, z to the fourth. Evaluate from 0 to 1. Well, plug in 0, you get 0. Plug in 1, you'll get 2 plus 1, which is 3. Almost made it. Okay, so this is equal to the integral from 0 to 2 pi of 3, which is 3 theta, from 0 to 2 pi, which is 6 pi. All right, and I should have put z equals 0 to z equals 1 there. All right, so again, this one's actually fairly straightforward. It just says, hey, keep in mind, you can change your order of integration on cylindrical coordinates should a certain shape fit your needs. All right, let's do another one. Let E be the solid region bounded below by the cone z equals square root of x squared plus y squared, and above by the inverted cone, also known as upside down cone, z equals 4 minus the square root of x squared plus y squared. So our shape, I'll quickly sketch it, is you have a cone that goes up, doing something like this. And then you also have a cone which goes down. So maybe it starts here at 4. Does something like this. And we want to be between them. And so what our shape turns out to be is this kind of thing right here. Okay, so there's our solid. It's between these two cones. All right? Can you see it? Between those two cones? Okay. Now, there's our solid. Ooh, it's a solid. And S is our boundary of the solid, outward pointing normals, and we want to find the flux. So you notice it didn't write F dot n. It didn't have to write F dot n because it said the word flux. So that says, all right, what we're looking for is the integral on our surface of F dot n. Well, we have all our pieces in place. A flux through a surface of a solid. So we use divergence theorem. That's the integral over our solid of the divergence of F dV. Okay, well let's figure out what does that turn out to be. That's the integral over our solid of our derivative with respect to our first slot with respect to x, nothing. Come to the second one, derivative with respect to y, well, x squared. Go to the last slot, derivative with respect to z, nothing. All right, so we get the integral of x squared dv. And now you're thinking, ha-ha, we can get symmetry, right, Steve? Right? No. The symmetry doesn't cancel stuff out. Why? Notice what's true about x squared. It's never negative. You can't get cancellation when you have two positive things. It's not like, oh, I have a positive thing, and if I go across the other side, it's still positive. And I was like, oh, well, I guess twice as much to love. Okay. So we have to integrate. What's our coordinate system? Which, cylindrical, yeah. A cone at the origin works pretty well in spherical. A cone away from the origin does not work for spherical. So this is going to be cylindrical coordinates. And if we slice, what we'll see is our bottom cone corresponds to z equals r, and our top cone corresponds to z equals 4 minus r. And I'm just reading off z equals r, z equals 4 minus r. So what we're doing is we're spinning this piece around. Where do they intersect? Well, for which value of r does r match 4 minus r? At 2. So what do we get? Well, our bounds are 0 to 2 pi for theta, 0 to 2 for r, and then we go from r up to 4 minus r, r up to 4 minus r for z. There we go. So this is integral, integral, integral. What does x squared become in cylindrical coordinates? R squared cosine squared, because x is r cosine theta. dv is still r dz dr d theta. We got 0 to 2 pi for our theta. R goes from 0 to 2, and z goes from r to 4 minus r. So, well, we start integrating. The first layer is pretty easy because there's no z. So we still have the r cubed cosine squared, then z, evaluated from z equals r up to z equals 4 minus r. Well, when you evaluate that, you're going to take 4 minus r, subtract r. So we're going to get 0 to 2 pi, 0 to 2 of r cubed cosine squared. All right, that's 4 minus r, subtract r, which is 4 minus 2r. So we can multiply the r through. So that's 0 to 2 pi, 0 to 2 of 4r cubed minus, let's see, what is that? R to the 4th. Yeah. Cosine squared theta d theta. All right. Which becomes, well, here, whoops, I forgot my dr. I'm sorry. Going quickly, you should slow down. You have the integral from 0 to 2 pi of cosine squared theta d theta. And then you're going to add on to that the integral from 0 to 2, not add, multiply. Multiply. Now I feel like I'm a Calc 3 student who wants to turn multiplication into addition. It doesn't work that way. Okay, so we can break it up. Now the integral of cosine squared, the way you would do that, I'm just going to quickly talk you through it. It'd be 1/2 plus 1/2 cosine 2 theta. And if you integrate that from 0 to 2 pi, this would be pi. Yes, it is minus 2r to the 4th. In this integral, you would get r to the 4th minus 2/5 r to the 5th from 0 to 2. If you plug in 0, you get 0. If you plug in 2, you get 16 minus 64 over 5, because 2 to the 5th is 32 times 2 is 64, which is 80 over 5 minus 64 over 5, which gives you 16 over 5. And so if you work this through, you'll get 16/5 pi. The last step is not too important. Okay? Our last example for the day. Let E be the solid region bounded below by the sphere x squared plus y squared plus z minus 1 squared equals 1, and above by the cone z equals the square root of x squared plus y squared. And let S be the surface and boundary of E with outward pointing normal vectors. Well, they're always outward pointing. Find the flux of the field f of x, y, z, 3x plus yzi plus xej plus e to the yk through s. Now, again, we see it's a flux problem with a solid. So those are our two things. When we see those go together, we say this is the divergence theorem problem. It's probably going to help us figure out what to do once we see the shape, but let's just go ahead and jump to the punchline. We say, all right, our flux by the divergence theorem is equal to the integral over our solid, which is called E, of the divergence. So I'll call that div of our 3x plus yz times I plus xz times j plus e to the y times k. Okay, so we're taking the divergence of that, dv. So that's the integral over our solid. So we come to our first slot, take the derivative of that with respect to x, and we get 3. Go to our second slot, take the derivative of that with respect to y, and we get 0. Go to our last slot, derivative of this with respect to z, 0. So we get that it's the integral of 3 dv. So in other words, this is equal to 3 times the volume of E. So we've actually done, in some sense, the problem, right? Well, maybe. Let's see if we can figure out this shape. So we have x squared plus y squared plus z minus 1 squared. Now that tells us we have a sphere that's been shifted to 0, 0, 1, radius 1. So if here's 0, 0, 1, radius 1, it just is nestled right there on the xy plane. So there we go. There's our sphere on the xy plane. Now, hold on, we're not done yet. It's bounded below. So that means we're below, the bottom part is the sphere. What's the above? And it's above by the cone, z equals the square root of x squared plus y squared. So there's that cone, z equals the square root of x squared plus y squared. That's the above. Well, wait, what's that shape? Well, if we stare at it, we say, all right, where do they intersect? The cone will actually intersect the the sphere, at the equator of that sphere. So our shape is kind of a strange one, maybe not one we're used to seeing, but it has the following form. So we have our half sphere, hemisphere, that's our bottom shape, and then we cone it out. So maybe it's easier to see what's happening in a cross section. So imagine we slice down, and what we'll see, if we look in the xz plane, is we see our sphere and our cone. Okay? So there we have well, xz, yz, probably better call it rz. So what we've done is we've taken this shape and we've spun it. And whatever that area is, well, that's the area that we need. Now, we could do this without doing any integration if you know some basic facts about shapes. So what are some basic facts about shapes? Well, one basic fact is that the volume of a sphere is equal to 4/3 pi r cubed. So that's if you have a sphere of radius r. Now, the other basic fact you need to know is that if you have a cone and it has height h and radius r, then that volume of that cone, that's equal to 1/3 pi r squared h. And if you combine those two together, you can say this is a half a sphere. Well, a half a sphere, that's 2/3 pi r cubed, and it's a half a sphere of radius 1, so 2/3 pi 1 cubed, so a half sphere. And then what do? Well, then we're going to subtract out a cone. Well, in the cone, the height of the cone is 1, radius is 1, so r and h are both 1, so minus 1/3 pi, this is our cone, to give us a final answer of 1/3 pi. All right, now you're probably thinking, well, that'd be awesome if I knew all those formulas and I thought about everything in a geometric way. What if I didn't think everything in a nice geometric way? Oh, you should try it. It's good stuff. It's good stuff. Once you get going, you never want to go back. But okay, let's do it integration-wise. Let's see if we get the same answer of 1/3 pi. I hope. All right, now that's the volume. Remember, what do we want? We want 3 times that. So our final answer, we claim, is pi. Now, let's go back. Let's see what we have. So, what coordinate system should we use? Well, I think we should use spherical coordinates because we have, this is a very nice cone. In fact, in spherical coordinates, we'd call that phi equals pi fourths. The sphere, you might say, wait a second, that's not centered at the origin. Sphere is centered at the origin. Ah, beautiful, beautiful. Sphere is not centered at the origin, not always so good. While we're down here, well, no, this is phi equals pi halves. Now, but we do know it's centered at z equals 1. If you come into this equation, you were to write it out, you get x squared plus y squared plus z squared minus 2z plus 1 equals 1. Cancel the 1s, move the 2z across. Then you get x squared plus y squared plus z squared equals 2z. Well, this is rho squared. And 2z is 2 rho cosine phi, because rho cosine phi equals z. So then you cancel a rho, and you get that rho equals 2 cosine phi. All right, so where do we go from here? So what we have is we're going to do this in spherical coordinates. So the volume would be equal to integral, 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 and then we're going to integrate 1. So if you integrate 1, then that's the volume. And our dv, well, that's rho sine of phi, d rho, d phi, d theta. There we go. Where does theta go between? Well, we're going full circle. See, full circle around 0 to 2 pi. What about phi? Well, we already mentioned pi fourths to pi halves. So, there's our range for phi. Pi fourths, pi halves. Now, what about rho? See, rho, you come up from the center, and you go until you hit. In this case, we hit the surface. Rho equals 2 cosine phi. All right, so now we integrate. Well, we can do at least one little thing to make our lives a little bit simpler. See, the theta, there is not very much theta, so you can actually pull that all the way over to here. And then what you get is you get a 2 pi, so that's good. That'll be at the start. You're probably already like, ooh, that's already too big. We need a third. Well, don't worry. We got plenty of space left. We got pi fourths to pi halves. Now we're integrating with respect to rho. 1/3 rho cubed sine phi, and then we're going from 0 up to 2 cosine phi d phi. So, and remember, this is actually rho equals 0 to rho equals 2 cosine phi. Now, if we do that, what do we have? Well, we have our 2 pi, and now we have our 1/3, so I'll go ahead and pull that out, rho cubed. Well, if we cube that, well, rho cubed, that's 8. I'll go ahead and bring the 8 out. Then we have a cosine cubed phi times a sine phi d phi, going from pi fourths to pi halves. All right, so now we're up to 16 pi thirds. And I probably should write pi halves when I said pi halves. All right, well, we're not nervous yet. Not nervous yet, because we still have to do this integral. Now, it looks terrible, but notice it's actually just a single sine, a bunch of cosines. So that says make a substitution. U equals cosine phi. And what does du become? Negative sine phi, d phi. So what do we get after making that substitution? We have 16 pi over 3. And then, what do we have? Because it's 16 pi over 3 is this part. Integral. Now, our bounds. Cosine of pi over 2 is 0. So that's 0. Cosine of pi over 4, well, it turns out that cosine of pi fourths, we say root 2 over 2, we can also write it as 1 over root 2. So 1 over root 2, all right. And now we have our u cubed minus du, so minus u cubed du. Now, of course, we can get rid of the minus by going back and flipping the bounds. So we have 16 pi over 3 times the integral from 0 to 1 over root 2 u cubed du. And we ran out of space, so let's finish it up over here. The integral of u cubed, well, that's not so bad. That's u to the 4th over 4. And then we're going to evaluate from 0 to 1 over root 2. So when we plug in 1 over root 2, 1 over root 2 to the 4th is the same as a half squared, which is the same as a 4th. And there's another 4th. But then there's a 16. And so all those things cancel except the pi and the 3. And of course, you plug in 0, you get 0. And so the volume is indeed pi thirds, which is what we said. So yeah, use geometry if you can. And if you can't use geometry, you always got integration to fall back on. And it's never led us wrong before, I hope. Well, probably not. But okay, got a nice fun problem. And of course, we're going to do a lot more practice next time. So come back and we'll see a lot more of these types of problems. All right, have a good day. Bye.